Okay, we're going to construct a proof of the Pythagorean theorem. To construct the proof, I've included, I have 4 pieces of paper here that all have a right angle corner to them. And so well, maybe before we even start the proof, maybe what we should do is make sure that we understand what it is we want to show. So what do we want to show? Well, the Pythagorean theorem says that if I have a right triangle whose sides listed, let's say, in order of magnitude are A, B, and C, then the following relationship is true about A, B, and C: A squared plus B squared equals C squared. So that's what we want to show, and so let's go ahead and sketch out a proof. So this particular proof requires you to start with 4 congruent right triangles. So I'm going to construct just an arbitrary right triangle by cutting off the corner, I guess, of this particular piece of paper, which is quadruple. There are 4 of these. Cut those. Okay, we got those all cut out. We've got our 4 congruent triangles, 1, 2, 3, 4. I'm going to go ahead and label them up so that I know how to talk about them. So this would be side A, B, and C. 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 Now, since they're congruent, of course, we would also recognize that all of these angles, let's call them angle 1, are all the same. It was constructed as a right triangle by cutting it out of the corner, a piece of. So that's a right angle there, and these would all be angle 2s. Okay. So now that the idea is to somehow construct a figure that we might be able to make some sense out of. So I'm going to go ahead and get my glue stick out and start by constructing a figure whose area we can maybe then take a look at. And so let's put this piece here, and I can see that once I have that piece kind of glued down, it makes kind of sense to me that we might want to think about constructing this figure, because once I have that figure constructed, I can see it looks like a square, and a square side length is C, so the area of that square is C squared, so maybe we could relate it somehow then to the A squared plus B squared through some sort of algebraic process. So let's go ahead and try that. Go ahead and glue that guy down. Go ahead and glue this one down. And then I'll go ahead and glue this piece down. That's kind of a neat figure. It looks like we have a square on the outside and a square on the inside. Of course, we'll have to justify that somehow. Let's go ahead and take a look at the figure. So right away we know that if this is a right triangle in here, sides A, B, and C, then these angles 1 and 2 would have to add the 90 degrees, because the sum of the 3 angles in the triangle, of course, is 180. So the sum of the 2 non-right angles would have to be half of that 180, because the 90 is taken up here. So 1 plus 2 is going to always be 90. So the 2 angles that are non-right in a right triangle are complementary. So that means what we have here in this corner then must be a right angle, because the angle 1 and 2 in this triangle are 90, and this angle 2 is the same as that angle 2. So this angle 1 and 2 will have to be 90 as well. So this is indeed a square, and the square has side length C, since the hypotenuse of each right triangle is on the exterior of the square. So right away we can say, well, one way that we can calculate the area of this figure would just be to consider it as a square whose side length is C. So this area calculated one way is just C squared. But another way that we could figure it is to take a look at its parts and pieces. So another way to look at it is as 4 right triangles. So there would be 4 right triangles. Now each of these right triangles has a height and a base, and we know that the area formula for a right triangle, or for any triangle, is 1/2 the base times the height. So in this case, the bases are all B's and the heights are all A's. faces and heights. Of course, B and A could be considered, I guess, interchangeably. So that's the area of the pink triangles. Now the question is, well, what's the area of this thing in here? Because we're obviously missing something in the middle if we just consider the triangles. And here we have to consider, well, we need to know what the shape is. First of all, it sure looks like a square, but how do we know it's a square? Well, we know it's a square because this line on this particular triangle here is straight, and it's intersected by a line belonging to another triangle where there's a right angle here. And so since we have a straight line, right angle, straight line means that we have 180 degrees along that straight line at this vertex. So indeed that must be 90, because 90 plus 90 is 180. So we do have right angles everywhere in that interior figure, so it is a square. So all we need to know is what one side's length is, and we can square that. And this is where it's a little bit maybe tricky to see exactly how to write that, but here's the idea. The whole side length of this triangle on the bottom here would be B. So this whole length is B, but it's being cut short. B is being cut short by this side length A. So if I want an expression for what this side length is, I would just call it B minus A. And since that's B minus A, and this is B and that's A, so this one would be B minus A as well, and it's indeed a square. So the square side length would be B minus A times B minus A. Everybody understand that? So this one would be B minus A as well. Okay, so now let's go ahead and do some simplification. 4 times 1/2 is 2BA. And I can see that I have binomial times a binomial, so I'll double distribute the binomial across the binomial and call it B squared minus 2AB plus A squared. And we can see that the 2BA and the 2AB are like terms, one positive, one negative. Those will go away. And I'll go ahead and commute the resulting sum and call this A squared plus B squared. And it looks like we've got ourselves to the point of a proof, because the area computed one way is C squared, and computed another way is A squared plus B squared. So just a little bit of clearing that up. So since A2 is equal to A1, we have A squared plus B squared equals C squared, and we have shown what was desired.